what you should know.
About atoms and molecules. Let's start with the atom. Atoms are what makes up all matter. They are defined as being the smallest unit of an element that maintains the properties of that element, or the smallest unit of matter that doesn't involve generating charged particles. Within the atom, there are subatomic particles with special properties. Protons and neutrons are subatomic particles found in the atomic nucleus, and electrons circle the nucleus in a cloud. The three major subatomic particles have different charges. Protons are positively charged, electrons are negatively charged, and neutrons have no charge. A common simple representation of an atom is the Bohr model, which shows the electrons orbiting in rings called shells. In this model, the closer the electrons are orbiting to the nucleus, the lower energy they have, and each shell can only hold a certain number of electrons to be considered stable. The outer shell is called the valence shell. Another property to consider about atoms and particles is their mass. The mass of one proton is about 1.672623 times 10 to the negative 24th grams, or approximately 1 Dalton. Neutrons also have a mass of approximately 1 Dalton. Electrons are almost 2,000 times lighter, so when we think about the masses of atoms, we don't worry about them so much. The periodic table organizes elements by their properties, starting with their atomic number, going from 1 for hydrogen to 118 for oganesson. The organization of the rows and columns also tells you a lot about their properties, as we shall see. You can learn a lot about an element by looking at one square on the periodic table. At the top of the square is the atomic number. For carbon, the atomic number is 6, meaning every carbon atom has 6 protons. A neutrally charged atom of carbon will always have 6 electrons, so that positive and negative charges cancel out. The typical number of neutrons in carbon is also 6. Remember that protons and neutrons both have a mass of about 1 Dalton, but electrons have essentially no mass. Therefore, an atom with 6 protons and 6 neutrons would have a mass of 12. However, notice that the atomic mass of carbon, shown at the bottom of the periodic table square, is slightly more than 12. That's because the number of neutrons can change, making an atom of a different mass without changing the other chemical properties of the atom. Atoms with the same number of protons but a different number of neutrons are isotopes. Carbon has two other isotopes besides carbon 12. Carbon 13 has 7 neutrons, and carbon 14 has 8. However, they are so much less common than carbon 12 that if you average all the masses of all the carbon atoms in any carbon sample, you get an average mass of 12.011. When the number of neutrons and protons becomes too unbalanced, an isotope may become radioactive, meaning that it is likely to fall apart. Carbon 14 is an example of a radioactive isotope. We can also look at the periodic table to figure out how many electrons makes an atom stable. Recall that in the Bohr model of the atom, electrons are shown as orbiting the nucleus in shells with different energy. The first shell is full with 2 electrons in it, which is why in the first row of the periodic table there are just 2 elements, hydrogen and helium. The second shell is full with 8, which is why in the second row of the periodic table there are 8 elements, ending with neon. The third shell is a little tricky, but all you need to know for now is that it is also stable when it has 8 electrons in it. The fact that the second and third shells are both happy with 8 electrons is called the octet rule. Atoms with a naturally stable outer shell, such as helium, neon, and argon, are non-reactive gases. You can find these atoms in the rightmost column of the periodic table. All other atoms seek to have a full outer shell of electrons. They fill this shell by either losing or gaining electrons or by sharing electrons with other atoms. Atoms that only need to gain or lose 1 or 2 electrons to have a stable outer shell often form ions. Sodium, for example, only has 1 electron in its outer shell. If it loses that electron, its shells are now stable. Once that happens, it now has 1 fewer electrons than it has protons, giving it a positive charge. Chlorine, on the other hand, has an outer shell with 7 electrons. Adding just 1 more electron makes its outer shell full. Because the chloride ion now has 17 protons but 18 electrons, it has a negative charge of -1. Positively charged ions are also called cations. Negatively charged ions are also called anions. To help you remember, think of the fact that cats have paws. They are positive. Change one letter of anion and you get onion, which can elicit a negative response when they make you cry. By looking at the periodic table, you can tell which atoms are most likely to form ions. Losing or gaining more than one or two electrons is not typical because that would make the charge too imbalanced. Remember that the right column has elements with full shells. Any element in the second to right column just needs one more electron to be like the right column. So these are likely to form ion with a -1 charge. Any element in the leftmost column has only one electron in its outer shell, so it is likely to lose that electron and have a +1 charge. The elements in the second to left column have to lose two, so they have a +2 charge when they form ions. Once again, we are going to skip the more complicated electron chemistry that happens in anything beyond the octet rule in the third shell. The metals get weird and can sometimes form several different stable ions, like iron that can be either +2 or +3. But since we're focusing on biological chemistry, we're not going to worry about that so much. Ionic bonds are formed when oppositely charged ions associate to make ionic compounds. Ionic compounds are also called salts. The salt you are probably most familiar with is sodium chloride, commonly known as table salt. Sodium chloride forms solid crystals at room temperature. However, in water, the bonds between the sodium chloride ions are disrupted by the water molecules. This is true of all ionic compounds, though some dissolve more easily than others. Another way for atoms to fill their outer shells is to share electrons with other atoms in covalent bonds. Carbon only has 4 electrons in its outer shell. Gaining or losing 4 electrons to form an ion would be very difficult because it would give it a large positive or negative charge. Hydrogen has 1 electron in its outer shell and wants two. In methane, carbon binds to 4 hydrogen ions. Each hydrogen shares its electron with carbon, and carbon shares 1 electron with each hydrogen. In this way, all the atoms have full outer shells and are stable. Remember, what's really happening is that the electron clouds of these atoms are merging into one cloud. This interaction makes covalent bonds much stronger bonds than ionic bonds because the electrons circle around both nuclei in the bond. Electron sharing isn't often even. In methane, because the carbon nucleus has a lot more positive charge, it holds a bit tighter to the electrons than the hydrogen nuclei do. This imbalance is called a dipole. In symmetrical molecules, the dipole cancels out, so that the overall molecule is said to have a dipole moment of zero, or to be non-polar. Oxygen only needs 2 electrons to fill its outer shell. When it forms covalent bonds, it shares 2 of these electrons, but the other 4 are tugged to its nucleus. When it bonds with other oxygen atoms, each atom shares 2 electrons with the other to form a double bond. However, the other electrons are evenly tugged to each side of the molecule, so oxygen molecules are symmetrical and therefore overall nonpolar. This is also true for carbon dioxide. However, when oxygen forms bonds with hydrogen in water molecules, hydrogen just can't compete with the strong electronegativity of oxygen. The electrons that oxygen clusters on one side push the nuclei of the hydrogen atoms away. This molecule is now asymmetrical because of the uneven distribution of electrons. It ends up with a slight negative charge on one side and a slight positive charge on the other. This molecule has poles to it, like a magnet, so we call it a polar molecule. Because polar molecules have a slight charge at each end, they like to interact with other molecules that also have a charge, like other polar molecules or ions. Here are some examples of nonpolar or polar molecules. Note that the nonpolar molecules have symmetrical bonds, where the polar molecules are asymmetrical, showing the uneven distribution of electrons. Some covalently bound molecules can also be ions. Even though their bonds involve shared electrons, they have fewer or more electrons than their overall number of protons. These are called polyatomic ions. Important polyatomic ions in the body include hydroxyl, phosphate, bicarbonate, and ammonium ions. Like other ions, they can form salts with ions of the opposite charge. But when these dissociate, the covalently bonded polyatomic ion stays together. The charged ends of polar molecules can be attracted to the oppositely charged ends of other polar molecules. These are called hydrogen bonds because they often involve the hydrogens and oxygens of water or hydroxyls. Due to the partial charges involved, hydrogen bonds are weak interactions compared to ionic bonds, but can be very strong when they are added together. Many large organic molecules rely on hydrogen bonding to form into their proper shapes, or to create strong interactions with other molecules. Even nonpolar molecules interact with each other through dipole-dipole interactions because electrons in these bonds move around and sometimes create very weak, very temporary charge differences. These weak interactions are called van der Waals interactions. Like hydrogen bonds, they can become very strong forces when they are added together. There is one last thing to mention before we leave this video. Take a look at these groups of atoms. They look like the polyatomic ions we discussed previously. But now we've swapped out one of the hydrogens for some mystery large molecule. These are called functional groups. The idea behind them is that this collection of atoms maintains certain functional properties no matter what it's attached to. For example, in water, amino groups retain a positive charge on the nitrogen, and phosphate groups often retain negative charges on the hydrogens, which makes anything these groups attach to have those charges. Hydroxyl and carboxylic acid groups have asymmetrical polar carbon oxygen bonds, which will make whatever these molecules attach to have polar properties at that location. One more group that's important to know for biologists is a methyl group. Remember, methane is a nonpolar molecule, so any molecule that a methyl group attaches to will be nonpolar, whatever that group is. In fact, any length of carbons linked together in a chain will make that part of the molecule nonpolar.